And then actually, all right. Because I need Sophia or Emma to ask me questions. Maybe Ryan, you could try. I mean, you won't have any. Need questions. So here we go. So let's start with what happened last time. Exact area. Very good. Exact, not approximate. Very good. That's a good question. Let's just keep going. Of a region. What's the region? Question. Something under the curve. Yeah. So here we go. This is the region. All right. So exact area of a region is what? It is the height of the function. Let's give it. Oh, should I use this? I guess I must have used k. I don't remember. All right, I'm gonna use k here. So, height of a function. Questions? This is our k, height of our function times the what the hell is that? Very good. And the answer is that this thing equals okay. We're gonna be doing Riemann sums. We will be doing Riemann integral. We're gonna do the Riemann rather than Lebesgue, whatever that thing is, and there's a third one. Is there a new one too after that? Lebesgue, that dude. Lebesgue. There is Sophia. Okay, we were waiting for you. What? I need questions, and Ryan was giving me fake questions. But they were not bad, actually. I appreciate your questions, Ryan. Okay. So this thing here is xk, and then this is xk, and this is k minus 1. All right. So folks, so this is the kth rectangle under the curve. And if we did this, what happens? So this just randomly is the kth rectangle. In other words, what this is just this thing here. And let me do this. And Sophia, get ready to ask me all kinds of questions. Very good. Thank you. God bless. All right. So here we go. This is xk. This is xk minus 1. And then this guy, we're going to call this point here. So right now, all we have here is, actually, I'm going to take this off, the delta thing, and just put that up here. Okay, so what is this? Ryan, sorry, go get your homework out, but what is this? This thing is the height of this rectangle times the width of this rectangle. So this is actually area. Very good. All right. And it is an area of which rectangle? Area of the kth rectangle. We're just doing math literacy today. So now what happens is, if I come in and put the sigma here, and I say that K starts at 1 and goes all the way to N. I did not start recording this thing. No, I did. Oh, it is recording. Is it? Yeah, it is. Good. All right. Thank God. Now what's happened? Miss Sophia, I like your hat, but you need to answer. So before I put the sigma sign, all this thing was the area of the kth rectangle. And now the situation has changed. I've put the summation sign here. And now K actually goes from N to, from 1 to N. So in fact, this whole thing is, so give me the first term here. Yeah. F, K, X. And then here what? The 1. Very good. The, and then K is still 1. So this is going to be for K equals 1. So this is 1 minus 1. This is review. Oh, that's X. Okay. Yeah, that's X. Very good. And then this means sigma summation. So we're adding plus. Very good. So maybe it's this one here. And so we're going to have K as 2, the second rectangle. So that's the height. Very good. Very good. And then dot, 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 plus all the way to N. And you agree? So N is just the number of rectangles. Yeah, N is a natural number. And we are saying N can be 18, N can be 4, N can be 222, and eventually goes all the way to infinity. Right? Okay, now that's what this is. And what I have on this side, it says exact area. Is this the exact area? And the answer is this thing. This gives you the sum of n rectangles below this curve here. And I think it is not yes. Because n is not, because the triangles have to go in the limit. In the limit, when there are so many rectangles underneath this red curve, that they fit in perfectly, so that they cover. Because right now, where is the error? This one didn't get captured. Let's say these are n. Exactly, that is where the limit thing comes in. So once I do this, I bring in the limit, and I go when n goes to infinity. So that means K starts from 1 and keeps going forever. So in the limit, as n tends to infinity, the number of rectangles under the curve becomes so numerous that they end up. So how many do we have here? 1, 2, 3, 4, 5, right? As n, then it's the number of rectangles is 5 right now. As n goes to infinity, we're going to have little ones here. You see that the error is getting smaller. Now the error is only this much. So smaller and precise. There are other ways to do it. This is just generic. Yes. Mm-hmm. Oh, so what happened? So I was looking at this and I must have copied it from a textbook from Simmons, and I was like, I didn't like that because we have k here and we have this. This should be n and this should be infinity. Oh no, but no. That is correct. This becomes infinity. What's your question again? Sorry. Oh, deltas are shrinking because yeah, that this thing becomes smaller. So that's where the norm of the Riemann integral comes in and explains all of that. So this is just a very, so you know this thing. So the norm of the partition. So this thing here. This is the largest width of the subinterval is then less than delta. So this is one of the conditions. And then the difference between this and the exact integral better be less than epsilon. So that comes in. This is just a very vague, not precise way of just thinking about this represents an approximation, and then this whole thing becomes exact because the limit was applied, and when it becomes exact, we can actually, we can write this as using the integral sign. Yes, Sophia? No? Okay. Do you understand all of this notation here? This is saying that if you take the sum of n rectangles, and rather than the sum of areas of n rectangles, sum of areas of rectangles that go on forever, almost forever to the infinity, that many rectangles under the curve, then the area given by one of these, when added together, is the actual area, as if we were not using rectangles, but we were able to figure out. Which one? Oh no, it was not an exact area, but approximate area. Sorry. So this gives you an approximate area because n is not large enough. When n becomes super large, imaginatively imaginatively large, then we get the exact. Okay. All righty. Okay. Now let's do. That's a good point, Mr. Ryan. I'm going to think about. I'll have to go back to Simmons' textbook and see what he exactly did, so that because he wasn't doing Riemann, the Simmons textbook is just the introductory textbook, so it's not analysis textbook. This distance has to become smaller because now we're crowding the area under the curve with so many more k's you have, the narrower the rectangles are going to be. And that idea gets captured with the norm. Yeah, but not here. There is, you can't really see it. You just have to imagine more and more of them. Yeah, it's not precise math at all here. This is kind of like conceptual physics. We do, I think in regular calculus, we do Riemann sums and then they skip the definition of Riemann integral, or do you guys do that in calculus? No, okay. No. All right. And there's some more confusion that are coming up. So be ready unless we run out of time here. Okay, so last time we did partition. And what I'm going to do is go straight to, so our P today is going to be this thing here. P is going to be made up of, let's see, I minus 1. I'm going to copy paste from here. I'm jumping a little bit just to make it more fun. All right, what do I have here? Sophia, you're on the, oh, thank you for saving it. So I have a set P, and inside that set P, I have one thing that looks like a closed interval, an interval, right? In which if I was 1, then this would be 0, and I goes from 1 to n. So if we expand this thing, today we're just doing language because it's raining. Okay, so give me, so this is kind of a formula that helps us generate the set with actual elements in it. So what's the first element? I goes from 1 to n. So x, I would be, our first element, i's value would be 1, so it will be 1 minus 1. And then this would be 1. This is our first interval. Second one, I would be 2. Okay. And let's go to n. So I want you to do n. So n is going to be here, right? N minus 1. So this is the previous one. This is the last one. So how many subintervals do we have here in this set P? So it's a partition made up of n subintervals. 1, 2, 3, all the way to n. What is this number n? It's an integer. It could be 100, 1500, it could be 3 million, but it's not infinity. It is, the key thing to remember is this is a finite set, because n is a finite number. Okay, now how do we represent this? So let's say this is A. This was the thing that got partitioned into these subintervals. So this would be x naught, and this would be xn. So x naught is here. X1 could be anywhere. So I'm going to throw it here. All right. So what's the next number I should put on there? Very good. X2 goes here. It can be anywhere. X3. Let's say X3 is here. And then we need Xn is already here, right? And then X minus 1. to the one previous to that. So therefore, now we have what? We have, these are the subintervals. How do I do that? Yeah, right here. These are the subintervals. This guy comes here, so it's x0 minus x1. This one, and you notice what? These two guys are the same. Yep. And these two guys are same. Dot, 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 between x3 and n minus 1, there are a bunch of these. And so we put one right here. And very good. All right. This oh, this is wrong. These are just the subintervals. Okay. Now, so this is, let's see, tagged. So this is called a partition, which has subdivided the closed interval AB into subintervals. This guy here is a subinterval of AB. So is this one. These are under. These subintervals make up AB. Yeah, okay. Now what do we do? Now the other ideas, this is all very abstract. Let's choose a point in the the first subinterval, and let's call it T. So I'm going to choose randomly this point, and I'm going to call it T1, tag. T is for tag. So what's happened to the first subinterval? It has got tagged. You can choose anything. You can choose the right endpoint of the subinterval, the left endpoint of the subinterval, anything in between, right in the middle. Let's go for right in the middle. So this is a number we chose. We're calling it the tag. Tag is that number that if we drew a vertical line from it going up, it's going to hit the curve somewhere. And rather than put in what we were putting in here, that was the height, right? This number that we choose will go in here and give us the height of the rectangle. Because what's going to sit on these subintervals? The rectangles under the curve. Okay, so we go here and choose, let's say this one right here, all completely random, T3. And for the last one, I'm going to choose the right endpoint randomly. And this would be Tn. All right, so this is a partition that has done what? This is a partition, this is a set. Everything, of course, is a set. This is a set of subintervals that subdivided the AB closed interval that we started out with. AB comes from this point here, right? This point. And it's between the curvy line, the two vertical lines, and above the x-axis. That's the area we're trying to calculate. All right, so make this slightly smaller. And this is 1. Let's make this 0. Okay, so Sophia, right now, we have tags. How do we include it into this set? Each one of these comes with a tag, right? Or very good, or you could put it after it. Because you got a subinterval because we have no way. If we put that in, there will be three things in a subinterval. Subinterval notation says put the endpoints, the left endpoint and the right endpoint. Comma, we put the tag that randomly we chose a number between these two endpoints, and then we can do this. What's happened? Now our partition before only had subintervals. Now our partition, at least the first subinterval, comma, has the tag that we chose randomly. Okay, so we have a ordered pair. We have an ordered pair of a subinterval followed by the tag that we chose, this random number, which will determine what height, what the height for this subinterval will be, wherever it hits. Okay, so we have a pair here, ordered pair, and then this again, and then we do T2 here, and then this guy will be Tn. All right, and now how do we? Before, if we just had subintervals, we were using P. When we say, so this was just a partition. When we put in the tags, then it becomes a tagged partition. So now what we have is called a tag partition. And to represent that, we put a dot on top. Okay, so what happens is this. We are going to have, this will be our first rectangle, actually right here. This tag will determine how high the rectangle is going to be. This tag, I stuck it in the middle, right? So our second rectangle that will sit on the base on these subintervals, its height is going to be like that. And this T2 takes us right up to that curve right there. So this area plus this area, and then for 3, and then dot, 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 and then here, it's going to be all the way up to here, because Tn is what I chose, the right endpoint. So these are rectangles with bunch of rectangles here. If we add up all the areas of these rectangles, we get what? Zara, we add up the areas of this rectangle, we get the approximate area of the region under the curve. All right, are you lost, child of Sophia? No, very good. All right, let's move on. So now, what's a tagged partition? Bunch of subintervals with randomly chosen point between them. And that gets us how tall our rectangles are going to be. Okay, and you can choose them in infinitely many ways. And now we are about to have some tragedy. So let's do this. Okay, I'll take this off. So I'm going to write an ordered pair. And I'm going to put F here. So this ordered pair has an F. Guess it's this guy here, right? The function F. I put the function F together with the tag partition that we see here. So I'm going. So how do I say that the graph of this function has a tag partition? Okay, and you know what this thing is called? And it depends on the book. Sometimes people use S. I'm going to use R here. because we're coming to the man who's responsible for all this, known as that psychotic dude. 10 people, Ryan, what is this thing? I've got the function, and then let's do a semicolon here. And I have the tagged partition, this thing, and there's the R. R is the hint, is the man. This is Riemann sum. This is Riemann sum. F represents the function. Okay, and then this represents the tag partition of the function. Because this is a very good question. This is a shorthand. This thing here is a shorthand for, wait for it, for, and I'm going to write it right here. So this is called Riemann sum. This is a shorthand for what I'm going to write here. Okay, and we've seen that before, which is the approximate area under the curve is what's going to go here. So this is where it gets interesting. And I want to make sure, and I put the dot here. So we have sigma, let's go from I equals 1 to n. And here's our height for each one of these rectangles. What goes in the mid into F? Cheat from this diagram. What input does the function take? Because it has a tag partition, so it's going to have what? Tx, because previously we had x sub k, right? We're not using x. We can use x or any point or the left x value. And so we randomly choose, and we, okay. Okay, very good. I'm going to give you the answer. Does that make sense to you? Yes. Very good. All right. So here's the width. We haven't got to that, but we got the height. We're not going to use x0 in there or x1 or anything like that. It can be x0. It can be x1. This could have been the t1, for instance. But we chose randomly this one here. This one is all the way to the side. So you randomly choose so that you can fit the tallest rectangle possible. Okay, all right. So let's do this again. So what goes there? Di. And because Di is 1, so we're talking about this length here. What's the second one? When we go to the second height, that would be T2, and it would be this length, shorter than that one. Okay, and then the width will be, this part is simple. Width of a sub-interval is, yes, very good. And so you take the right one, the bigger one, but we're using I. So I, yep. Yes? I did that too fast. Oh, this T1? And do not hit that. Very good.
Sure. Why is it at the?
Oh, sorry. So this is the tag partition, and it says that very good question, each sub-interval comes with its chosen tag, which is a number on the x-axis between the two endpoints of a sub-interval.
And why over here?
Because we choose one of these numbers to get the height. This is the height. And then this is the width. The tag, this number here, this tag determines how tall the rectangle will be. We always put the height and the width. That's the formula. All right. So that is very good question. Again, what is a tag partition? Subinterval with R chosen, randomly chosen in many infinite ways. The tag in number between, including the endpoints. Okay. All right. Okay, I think you're getting the whole thing, aren't you? Very good. And then that's it. That's Riemann's sum. And I think we should. Yes. I have no idea. We are over it. Yeah, it's time to end it because it's going to get more complicated. Because we're going to be taking limits. Umid, are you with Umid or? All right. Okay, guys. Thank you, Ryan, for the excellent questions at the beginning.